This is my third video lesson on Unit 5C. In this lesson, we'll be talking about intermolecular forces. Let's go to page 10 in the class packet. Motivation. Why doesn't the water spill over on the penny? From middle school, you should know that the reason is surface tension. So in this lesson, we'll explain how that works. Learning target. At the end of the lesson, I'll be able to explain and compare intermolecular and intramolecular forces. Announcements: there will be a homework free Junipod based off this lesson, and a quiz Junipod based off PowerPoint 1, 2, and 3. Intermolecular forces are basically the attractive forces we have been talking about in the previous units. They are the interactions of forces of attraction between molecules. They are responsible for the physical properties in a substance. So how does it work? If we look at these two molecules, how are they interacting with each other? Through opposites attract. Notice that the partial negative charge of one of the HCl molecules is attracted to the partial positive charge hydrogen of the other molecule. The prefix inter means among or between. So intermolecular forces is the forces of attraction between or among molecules. Another example of this will be interstate highway. So it's a highway between states. Intramolecular forces are also known as chemical bonds. For example, ionic, covalent, and metallic. They're the forces of attraction within a molecule. So basically, they are the bonds. So they're responsible for the chemical properties of a substance. They're much stronger than the intermolecular forces. The prefix intra means within. So intramolecular forces are the attractive forces within the molecule. So they are the chemical bonds. Another example of this will be intramutual sports. So let's figure out and draw the dipole in H2O. The first step is to figure out the partial charges of each element. So hydrogen has electronegativity of 2.2. Oxygen has electronegativity of 3.4. So the OH bond is a polar covalent bond. Since oxygen is more electronegative than hydrogen, it is partial negative and the hydrogens are partial positive. Since oxygen has a higher electronegativity than hydrogen and a partial negative charge, the dipole arrow will be facing oxygen. Since the dipole arrows do not cancel out, water is a polar molecule. Using the partial charges, draw 3 water molecules. Properly align them in the box below. So we already drew one water molecule. Let's draw another one. Notice that the partial charges of these water molecules are not properly aligned. You want to align them in a way that the opposite charges are facing each other. So therefore they can attract one another. So let's draw a third water molecule. Intramolecular forces are the covalent bonds in the diagram. They are the dark bold lines. The dashed lines represent the intermolecular forces. Keep in mind the dashed lines are used to represent intermolecular forces, and the dark lines are used to represent intramolecular forces. From the motivation, the surface tension you observe from the water on the penny is caused by the intermolecular forces of the water molecules. They are attracted to each other through the partial charges. There are different types of intermolecular forces. We are going to discuss and compare these 5 intermolecular forces for the rest of the lesson. So dipole-dipole interactions are the forces of attraction between polar molecules. So a dipole must be present. The more polar the bond, the stronger the dipole-dipole interaction. So here's a GIF showing what's happening. So you can see as the molecules get close to each other, they will interact through the partial charges. Check of understanding number 1. Which have a dipole-dipole interaction? Let's look at the first one. Here we have water in the solid state. Since water is a polar molecule, there is a dipole-dipole interaction. What if water is in the liquid state? Water in the liquid state is still a polar molecule, therefore there's dipole-dipole interaction. Water in the gas state is still a polar molecule, therefore there's dipole-dipole interaction when the water molecules interact. So the phases of the substance do not matter. What matters if it's a polar or nonpolar molecule. How about number 4? Is CH4 a polar molecule? The answer is no. CH4 is a nonpolar molecule, therefore it does not have any dipole-dipole interactions. How about HF? HF is a polar molecule, therefore it has dipole-dipole interactions. How about CO2? CO2 is a nonpolar molecule, therefore it does not have any dipole-dipole interactions. Learning check number 1. Which of the following have dipole-dipole interactions? Pause the video and resume once you complete it. So we're looking for a polar molecule. The only polar molecule is HBr, so the answer is choice 2. The next intramolecular force we are going to discuss is molecule ion or dipole ion. These two terms are referring to the same thing. They are the forces of attraction between the molecules and ion. Let's say we have a positive ion and a negative ion. The water molecules are going to orient themselves so that the opposite charges are facing each other. The partial charge of the oxygen is facing the positive charge sodium. For the chlorine, it will be the partial positive charge hydrogen that will be facing the chlorine. And they will interact with each other. So the dashed lines represent the molecule ion intramolecular force. Molecule ion is the strongest intramolecular force. How do we identify if something has a molecule-ion interaction? It's usually when an ionic compound is dissolved in water. For example, we have NaCl aqueous, so the ions are from this ionic compound, Na and Cl, and the molecule is coming from the aqueous, which is water. So you can see here, this is a molecule-ion interaction. So check of understanding number 2. Which of the following will have a molecule-ion interaction? Let's look at the first one. We have NaCl in the solid state. The answer is no, it only has ions. There's no molecules present. For Kf aqueous, Kf is an ionic compound, so there are ions, and aqueous means water. So that's the molecule, so there is molecule-ion interaction. For glucose aqueous, glucose is a covalent compound, and aqueous, which stands for water, is also a covalent compound. So they're both molecules. There's no ions here. So therefore, there is no molecule-ion interaction. How about NaCl liquid? So NaCl is the ion because it's an ionic compound, but there is no molecule. So there is no molecule-ion interaction. There is only molecule-ion interaction when it is an ionic compound dissolved in water. For check of understanding number 3, draw at least 3 water molecules aligned to each ion. So here are the water molecules. So again, you want the partial negative oxygen to face the positive ion and the partial positive hydrogen to face the negative ion. So here's a GIF showing the interaction. Learning check number 2. Which diagram best illustrates the ion molecule attraction that occurs when ions of NaCl, solid, are added to water? Pause the video and resume once you complete it. So the answer is choice 1. Learning check number 3. In which system do molecule ions attraction exist? Pause the video and resume once you complete it. So we're looking for an ionic compound that's dissolved in water. So the answer is choice 2, KCl aqueous. The next intramolecular force we're going to discuss is the hydrogen bonds. It is the forces of attraction between hydrogen of one molecule and the oxygen or nitrogen or fluorine of another molecule. So why only O, N, and F? Because O, N, and F have high electronegativity and a small radius. Hydrogen bonds are a special type of dipole-dipole interactions because it's basically opposites attract between the partial charges of the water molecules. So here's a GIF showing the interaction of the hydrogen bond. I am going to go over how to identify hydrogen bonds in 2 scenarios. The first scenario is pure substances, and the second scenario is in mixtures. The Regents usually only ask about pure substances, so in a pure substance, the molecule must have a hydrogen bonded to either a F, O, or N. Which of the following have a hydrogen bond in a pure substance? So does water have a hydrogen bond? The answer is yes, because it has a H bonded to a O. Does ammonium have a hydrogen bond? The answer is yes, because it has a H bonded to an N. Does nitrogen gas have a hydrogen bond? The answer is no, because there is no hydrogen. In the next example, does CH3F have a hydrogen bond? The answer is no, because in order for it to have a hydrogen bond, the H must be bonded to a F, O, or N. The H is bonded to a carbon, not an F. So this CH bond is nonpolar, so therefore there is no hydrogen bond. How about this one? This is formaldehyde. So does formaldehyde have a hydrogen bond? No, it does not, because the H is not bonding to the O, is bonding to the carbon, so therefore there is no hydrogen bond. In the next scenario, we are going to determine if there's a hydrogen bond in the mixture. So typically the regents will not ask you this. So in your mixture, you have two different molecules, A and B. A and B must fit these criteria. Molecule A must have a hydrogen bonded to F or N, and molecule B is a polar molecule with a polar bond with F or N. Check of understanding number 4. Will there be a hydrogen bond in the mixture? So here we have a mixture of NH3 and H2O. Will there be a hydrogen bond? The answer is yes. Why? Because NH3 and H2O fit the criteria of molecule A and B. How about the next example? We have formaldehyde mixed with water. Will there be a hydrogen bond? The answer is yes. Water fits the description of molecule A, and formaldehyde fits the criteria of molecule B. Notice that formaldehyde is a polar molecule with a polar bond with O. How about this example? Would nitrogen gas form a hydrogen bond with H2O? The answer is no. Why? Because nitrogen gas does not fit any criteria of molecule A or B. How about the last example? We have CH3F. If it's mixed with water, would there be a hydrogen bond? The answer is yes. Water represents molecule A, and CH3F represents molecule B. CH3F is a polar molecule with a polar bond involving F. Here's a GIF showing the hydrogen bond interaction amongst water molecules. So now I want you to pause this video and watch a TED video about the hydrogen bonds. Resume this video once you watch it. The video is in the description below. Another example of hydrogen bonds in nature is in DNA. Learning check number 4. Which of the following have hydrogen bonds interactions? Pause the video and resume once you complete it. The answer is choice 3 because you see an H with an O. The next intramolecular force is the ion-induced dipole. So it's a temporary induced interaction between an ion and a nonpolar molecule. Temporary means a short time, so only when the nonpolar molecule and the ion are close to each other. If they're far away, you will not see this interaction. So it is induced or caused when the charge of the ion causes the distortion of the electron cloud in the nonpolar molecule. Let's look at an example. Here we have CO2, which is a nonpolar molecule. It has uniform electron density in the electron cloud of the molecule. Then the ion is going to move close to the molecule and interact with it. Notice that the electron density shifts to the left. Electrons are negative, they will be attracted to the positively charged calcium. So the chlorine on the left has a partial negative charge, and the chlorine on the right has a partial positive charge. So here's a GIF showing the ion-induced dipole. So keep in mind, the ion-induced dipole interaction is temporary. So the moment the ion moves away, the interaction is gone. The last intramolecular force that we're going to cover is the London Dispersion Force. It's a temporary induced dipole when atoms and molecules come close to each other. Then when they move away, it is gone. In this example, we have two neon atoms. Notice that the electron density shifts when they come together. If one side has a high electron density, it becomes partially negative. Then the other side becomes partially positive. So you can see the opposites attract, and that is the London dispersion force. All molecules and atoms have dispersion forces. It is caused when two atoms and molecules come close together, they will polarize, causing the electron density to shift to one side, which causes an induced dipole, as you can see from this diagram. Nonpolar molecules only have this force of attraction. The term van der Waals forces is oftentimes refers to these dispersion forces, especially on the regions. On the regions, if you see the term van der Waals forces, it is referring to dispersion or London forces. So noble gases only have this intramolecular force as well. Dispersion forces are the weakest intramolecular force because it's only induced temporarily by the electron cloud in the atom and molecule. The term van der Waals forces can loosely refer to all intramolecular force, but keep in mind it is often and always applied to dispersion forces. Here's a concept map to help you visualize this. Keep in mind on the regions, van der Waals forces always refers to dispersion forces. Now I want you to watch a TED video about the van der Waals dispersion forces, so pause this video and watch the video in the descriptions below. Resume this video once you're done. Learning check number 5. Which type of attraction results from the formation of weak monetary dipoles? Pause the video and resume once you complete it. So we're looking for a weak intramolecular force, and monetary means temporarily, so the answer is van der Waals forces. Remember, on the regions, van der Waals forces refers to London dispersion forces. Learning check number 6. Which attractions are most prevalent between the molecules of HF in the liquid phase? Pause the video and resume once you complete it. The key word here is prevalent, which means dominant. This is important because every substance has van der Waals forces. Since molecule HF has a hydrogen and a fluorine, it is a hydrogen bond that is most prevalent. Here are the 5 types of intramolecular forces ordered by weakest to strongest. So dispersion is the weakest, then is ion-induced, then is dipole-dipole, then is hydrogen bonding, then molecule ion is the strongest. Here are the 7 physical properties that are affected by intramolecular forces. We will be discussing some of these in the next couple of lessons on how intramolecular forces influences them. Here's a summary table of each of the intramolecular forces and the intermolecular forces. The energy tells us how strong your attraction is. Remember, barf, breaking exort releases form. The stronger the attraction, the more energy you need to break it. As you can see, the intramolecular forces are usually stronger than intermolecular forces based off the energy. And here are some examples of each of the forces. For the first practice, I want you to identify all the possible intramolecular forces in each of the following. I will do the first 4 examples and then you can do the rest on your own. Water is a polar molecule, therefore it has dipole-dipole. Since there's an H and O, it also has hydrogen bonding, and every substance has van der Waals dispersion forces. CO2 is a nonpolar molecule, therefore it only has van der Waals dispersion forces. Since CO is polar, it has dipole-dipole, and it also has van der Waals dispersion forces. HF has hydrogen bonding. Since it's polar, it has dipole-dipole and van der Waals dispersion forces as well. So now you can do the rest on your own. Pause the video and resume once completed. Okay, so here's the answers. Now I want you to watch a TED video about surface tension and hydrogen bonding. So pause this video and watch it in the description below. Resume this video once you watch it. Surface tension is a film that is formed by intramolecular forces of water molecules. Check of understanding number 5. What type of intramolecular force is causing the surface tension of water? That is the hydrogen bonding. The surface tension caused by hydrogen bonding can hold light objects on top of the water. Cohesion is attraction between the same molecules. So the intramolecular forces between the same molecules is stronger than the intramolecular forces between different ones. In this example, water is forming stronger intermolecular forces with other water molecules than with different atoms on the penny. Adhesion is attraction between different molecules. The intermolecular forces between different molecules is stronger than the intermolecular forces between the same ones. In this example, the water molecules have a stronger attraction for the molecules in the glass than other water molecules. Check of understanding number 7. Does oil form intermolecular forces with water? The answer is yes, they form van der Waals dispersion forces. So why are there separate layers? Because water forms stronger intermolecular forces with other water molecules, like hydrogen bonding, than with van der Waals forces with the oil molecules. So is this an example of cohesion or adhesion? This is an example of cohesion. Check of understanding number 7. Like oil, alcohol is less dense than water, but it does not form layers when it's mixed. Why is that? Here's a Lewis dot diagram of alcohol. Notice that alcohol have a OH. Therefore, it can hydrogen bond with water. So unlike oil, which only has van der Waals dispersion forces, alcohol has hydrogen bonding. Therefore, even though alcohol is less dense than water, like oil, it can mix well with water thanks to hydrogen bonding. Viscosity is how thick your liquid is, how resistant it is to flow. In this example, we have water and honey. Notice that honey is more viscous than water. So what is the relationship between viscosity and intermolecular forces? There's a direct relationship. The more intermolecular forces, the thicker your liquid. So this concludes the video lesson for today. Remember to do the Juniper homework and quiz.